privileges of giving kind of review talks is you can generate completely, come up with completely wacky ideas. So I decided there's a new thing we need to talk about. It's called pure convective instability, PCI. So this was a lab experiment that one of my students, Michael Barry, did. And so what he did in the lab experiment is he had a tank full of salt stratified fluid. He had a mechanical grid in it, which moved backwards and forwards horizontally across the system. So there is no shear in the system. So the Richardson number in this experiment is actually infinity. It's stratified, but there's no shear. There's no mean flow, so there's no mean shear, so there's no. Essentially what happens is, it's kind of interesting, if you move the grid slowly, not much happens. But once you get above a certain level, this thing starts to create mixing as the eddies shed from the grid, the mechanical grid, and the density stratification evolves. There's an irreversible change in the background potential energy. He can measure all those things. And we can measure dissipation because there was a force transducer, so you can calculate the dissipation, stratification, and the other things. If you look at his results, you get this really weird thing that doesn't look anything like any of those other theories about shear flow turbulence. He said the rate of mixing was actually given by this very unusual looking formula that it's dependent, first of all, it's dependent on the molecular diffusivity and the viscosity. And you can see he ran it over quite a range. There's like 5 orders of magnitude variation in the ratio as he varied the intensity of the flow. And he defined a new length scale, now the 5th length scale, potentially. So I have 5 length scales, which is what he called the convective length scale, which is just a ratio of viscosity times the diffusivity of the background fluid and the stratification. This is a very good description of what this flows. It seems kind of odd, but there's a simple physical interpretation of this. If you accept this length scale here, this definition, his mixing formula is nothing other than the product. It's a mixing length theory. It's just a product of a dissipation to the 1/3. You'll notice that occurs here, and the length scale. I should add he varied the viscosity in the experiments as well as the stratification of that. So he varied everything except for the stratification, the diffusivity of the background fluid, but it was a salt stratified system. So a criterion for mixing in his pure convective instability experiments is that the convective length scale is bigger than Kolmogorov. If you play around with it, it just simply means that this buoyancy Reynolds number has got to be bigger than a Prandtl number. So you can have pure convective instability, introduces one other length scale. So does this apply at all in the ocean? I haven't seen too many mechanical grids moving around in the ocean lately. So one way to test this is to take his prediction and compare that with measured mixing rates in the ocean here. And so plotted on the vertical axis here is the Barry prediction of mixing rate from pure convective instability versus the Richardson number in these experiments. So if his theory was correct, all the data would lie along the dotted red line. And you can see when the Richardson number is small, it's truly terrible. It has nothing to do with describing the mixing rates. Interestingly, as the Richardson number gets bigger, towards 1 or larger, the data starts to, and these are the binned averages coming down, somewhat surprisingly, it starts to approach it, suggesting that as the Richardson number gets larger, maybe we start to approach pure convective instability. Now my scale here ends at 2, not infinity. Strictly his theory applies when it's infinite, but in practical terms, the suggestion is as this thing collapses, perhaps it means that in the ocean, if the Richardson number is close to 2, it's convectively dominated. You can also go to some other things which are kind of interesting. Using the Caulfield and Peltier definition, turns out you can use the results of Barry, and you can actually predict what this mixing efficiency is for a pure convective instability flow. And people are often fascinated by convective instability because it's very efficient potentially. And that's true. Turns out it's a function of these quantities here. So if you take an oceanic example, Prandtl number 7, and you assume the flow is very weak around, you can get efficiencies of more than 70%. On the other hand, counterintuitively, as the flow gets very energetic here, the efficiency gets very small. But you can see from the dots here that these convective instabilities appear to be actually quite rare in the ocean. So the hypothesis of what I'm saying here is that you can say that if in these two extremes maybe this applies, but in between the two there's actually something which I call a mixed mode. There's both shear and convection applying here. There are four length scales are important and only three, because if the convective instability is pretty rare, you don't need to worry about this other convective instability. You can test these ideas a little bit, which is using field data from moorings. You can actually measure, interestingly, Ellison scales, and you can show that there's a nice correlation between this complicated scale and a length scale, which is determined easily from a time series measurement, which is just a temperature or density variation divided by the background stratification, which leads to this prediction, because what we'd like to do ultimately is to use these ideas to predict mixing rates. And so if I summarize those data here, these data cover a very large range of, these are oceanic data covering quite large ranges of nearly 6 orders of magnitude. The vertical axis is what's measured from microstructure, and this is what's predicted from this very, very simple, and I defined a new term here, inspired by numerical people who use large eddy simulation. This is large eddy measurement, because it's actually, the only requirement is you don't have to measure the turbulence, but you do actually have to have a means of measuring overturning scales that are at the low wave number end of the turbulence. So it's large eddy measurement in that sense. I'll skip that, that's kind of complicated. But it turns out the nice thing about this is that you can generate from these moorings, therefore, very large data sets. And so from this particular data set, we have, and this gets to one of the key grand challenges I think we have, is how do we actually generate enough measurements to actually really infer what ocean mixing rates are. This comes from a water column that was instrumented over 30 meters. And if you dropped a turbulence profiler once, you'd have roughly about 10 to 15 estimates of mixing over the depth. From 10 days of moorings, we get nearly 60,000 independent estimates of mixing from this simple mixing length argument. So this suggests a way of, yes, and you notice the instantaneous, the variation, measured variations are huge, even though the median values tend to be it looks kind of logarithmic, and this is from this very energetic site, log normal. Let me close by one last thing I wanted to point out to you. So this is the same data you saw before. It's the field measurements and mixing, where I'm looking at this dependence on Richardson number. The whole point of these theories is that you would like to be able to use this to be described or using turbulence closure schemes in numerical circulation models for prediction of things like climate change and all. So this is just exactly what you saw before. Or if I plot it dimensionally now with the diffusivity plotted this way, it's the same data. I just haven't non-dimensionalized it for reasons that are... So these are field observations, and the blue dots are there. This is actually in standard ocean circulation models like ROMS and the MIT GCM. There's a number of choices. You know, as a modeler, you can just tick box 1, 2, 3, or 4, and you can run away with it. And to this day, the KPP scheme, which was proposed in the 90s, is still one of the standard choices and is very popular. And that's what the KPP scheme looks like. So my point in terms of the grand challenge is there seems to be a bit of a difference between what the closure scheme says and what the data actually says. In fact, there doesn't seem to be any relationship whatsoever between the two, which is a bit unnerve-wracking. So let me close by summarizing and asking a series of questions, since I don't have conclusions, but rather to stimulate your thinking maybe. Convective instability is a very seductive thing. People still try and understand it. But it would appear that if it's actually characterized by its occurrence by the Richardson number, it's actually pretty rare. So while it's potentially very efficient, I suggest you maybe it's not very important. On the other hand, I hopefully have convinced you that not all measurements in the ocean or the atmosphere are always done when the Richardson number is less than a quarter, which is what I would consider to be pure shear instability. I suspect that impure shear-driven mixing, again, I defined a new term here, which is kind of fun, is likely dominant. That is, a lot of the mixing can actually have characteristics of pure shear or pure convection, or more likely, a bit of both. Either way, it seems to me we need to actually measure the mean flow shear and all this. Which leads me to my next controversial point here, is we've spent years rushing around as knights in armor, trying to find out what the mixing coefficient is. Maybe it's just a red herring. Why don't we just bypass the whole thing, unless we absolutely need to, and just use simple models like Osborne-Cox, or alternatively, even more useful, these large eddy measurement method I'm talking about, which is obtained by Mooring, which has the idea of being able to generate very large data sets. So that suggests that we need to think about the way we measure turbulence. How do we get really long time series of estimates to mixing? Hopefully I've convinced you that closure schemes that are used in models should be looked at somewhat cautiously. They don't even, I suggest they're not even really that well tested, which is quite shocking considering how long they've been around, and something we need to think about. Either way, by looking and thinking about these questions, we need to actually get field measurements we're able to robustly test and hence develop true methods of parameterization and mixing, which are relevant for driving models, whether they're regional or long-term climate change models involved in this. So I'd really like to close by acknowledging my two principal collaborators, Cynthia Bluto, who's here somewhere today, and Nicole Jones, and thank you for listening to me. Thank you.
Thank you very much, Greg, for this very nice talk. We have plenty of time for questions. Bérangère?
Yes, whenever there is shear, normally you can use rapid distortion theory. What are predictions of rapid distortion theory on the mixing?
I just chose the one example of the KPP one because of its a standard parameterization that you can use within the suite that's usually available in the circulation models. So I can't answer your question specifically. I think the challenge is with any theory, whether it's like these or others based on two equation closure models or whatever, or rapid distortion theory, is we need to develop models that are robust and simple enough that they can actually be used in driving circulation models to predict flows and that. And that's a computational requirement ultimately. But also it seems important to me that the model should be transparent. Can you understand it in terms of what really are the physical processes? That's why these closure models that are typically in use are, quote, simpler than others. That DNS simulations and other techniques certainly give us lots of insight.
Hi, so this is more of a philosophical question. Because
I would expect less from you, Peter.
It never changed. So I'm influenced by working with Jim Riley. And it seems that underlying in all these arguments, this idea that the turbulent Froude number in both directions is of order 1 or greater, that it might be weakly stratified turbulence. And I'm wondering if you have any comments on this emerging concept of the strongly stratified regime, where the horizontal Froude number is much smaller than 1, and you have a vertical Froude number greater than 1, so there's these large quasi-horizontal pancake-like eddies driving shear and patchy turbulence, when now there's a new length scale, which is the horizontal length scale. Mm-hmm. And have you thought about any connections, or is this something you're interested in, or whatever?
It's a good question. I think the answer, the way I've approached this is that if I'm interested in the vertical mixing rate, then the thing I'm interested in is, in your terminology, is the vertical Froude number, because that's ultimately what's going to determine what's sort of ultimately determining flux across isopycnal surfaces. How that process is connected with lateral collapse, which is what you're alluding to, is certainly important. The other way of thinking about it is that in the real ocean flows, and I'm sure Matthew will talk about this, is the fluid's not at rest. There's incredibly complicated horizontal motions which are straining patches as well, background flow, let alone the dynamics of collapsing turbulent events. The second part to your answer to your question is, whatever the process is going, we need to actually be able to make measurements on long time scales, much longer than the evolution timescale of single patches. We need timescale measurements on very long time frames. And Hide Yamazaki will actually give a poster tomorrow where he shows an example of where you can use some of these mixing length arguments to actually answer questions about mixing on timescales of months, if not years. And I think that's where a grand challenge issue rises.
Okay, thank you, Greg. That was a great start. What I got from what you were saying was the KPP model is based on the philosophy that when it is sufficiently high Richardson number, mixing is switched off. And your work and the work that Claudia has done with outflows shows that you can still have mixing, but there's not much of it at higher Richardson numbers in some sense. But then there is this layered anisotropic stratified turbulence that Jim Riley and Lindborg and Billons and Schomas have predicted, and they say, well, you have these big pancakes of these spaceships going around, and they can still continue to do mixing. But the thing is, they do that very intermittently. It's when the spaceships touch each other that they have a little fight and they have a little bit of mix. The Richardson number goes down, and then it kicks off again. And so it's you mentioned the fact that your convective instability occurs but is rare. And surely the huge challenge is actually developing a census of what different kinds of mixing events you can have, how frequently they happen, and what are those characteristics of them. And it's actually it's my concept of the blind man and the elephant. Hearing what you say there's the shear driven mixing, and it has one kind of characteristic. And then you have this convective, what you're calling the pure convective, and it has another characteristic. And the real challenge is how frequently do each of them happen? Mm-hmm. Because we can identify a taxonomy of each different kind, but the question is how often do they happen?
Right. I totally agree with that comment, and hoping you would ask a question like that. I actually had one last slide. I assure you this is not collision. This is Cynthia produced this nice plot for me. So what you saw earlier is this is mixing as a function of Richardson number. So the blue dots are the ones you saw before. Okay. The orange ones are also estimates she made from the same mooring estimates, which gets to Colum's question about the frequency of events at varying Richardson numbers. And I think if you look at that, you can see the frequency is much higher for events at low Richardson number. It's less frequent as you get higher. And incidentally, this, if you asymptote this out, this turns out to be extremely close to the Barry prediction. The reason we don't have that there gets to a practical difficulty of measurement. The reason I didn't show you that before is we don't have a lot of faith in not so much the mixing rates, but actually the measurement of Richardson number in the field. It's very hard to measure the Richardson number at these high values accurately. Richardson number is the ratio of n squared over s squared. The n's okay, but you actually need to estimate s locally where a mixing event is occurring, which gets to Peter's question a little bit, with high precision. And that's hard because it gets to resolution of instrumentation that measures velocity, spatial separation, and the vertical. I show it there it does show that the events get less frequent as we go higher, but quantifying those histograms, and I don't know easily how to do that in the field. Numerically, it's not so easy either. It's very hard to generate high Richardson number sustained events in any numerical simulation, but that seems to be part of the challenge. They do occur in the ocean, but it's not all just happening between 0 and 0.25. That's absolutely true. So my view is pure shear, mixed mode, and by the time I get to the right-hand boundary, it's essentially PCI, my new term, pure convective instability. I want you all to write that in your next paper, please. It'll be sanctified by print.
In certain types of stars, it's the mixing is mostly caused by decorrelation of internal waves, and is not, even though there's shear, this turns out to be insignificant for the diffusion of species. So, I mean, could this also be possible in the ocean, that it's mostly driven by decorrelation of the internal waves? You don't need these other mechanisms.
Well, Matthew is probably the right person to answer this question. I'm sure he will when he gives his talk in an hour or so. Where's Matthew? There you, excellent, thank you. I don't know the answer to that question. the way that I have thought about it and the way I presented it here in our observations, whether they're based on small-scale waves or very large amplitude solitary waves, I didn't get into it, but the typical waves have vertical amplitudes of up to 80 meters in a couple of hundred meters of water. They're big, you know. There is localized shear events during the phase of the wave, but to say it was a decorrelation process, not so much that. It looks more like there are periods when locally the shear or the convection, incidentally, if it's convection, it means there's locally some Rayleigh number that actually has to go above a minimum value, which is arguably of order of a few thousand. But neither of those are what I call a decorrelation process. They're more associated with I have events which can generate potentially locally irreversible mixing. But I'm not an expert in that, so I'm not sure to answer your question properly.
Thanks.
Thank you for the talk. I have a comment more than a question. It's the final length scale you discussed with your experimental approach with the grid that was steered in the tank. The length scale you provided is actually generic, and you don't need turbulence to define it.
That's right.
And it's strongly controlling flows even at 0 Reynolds number. So there are studies of people doing moving objects in stratified fluid where the length scale nu kappa over n square power 1/4 is the length scale that control the shape of the flow around the body.
Yeah.
So my question is, how do you relate this turbulent thing to the shape of the flow related to mixing diffusivity and stratification?
In the grid stirring experiments, there are two parts to answer your question. If you take that length scale and you define a Rayleigh number based on that length scale, the conventional Rayleigh number for a continuously stratified fluid n squared L to the 4th over nu kappa, it turns out that in his experiments, the minimum value of Rayleigh number for him to get internal convective instability, which is what it is around about 1,000. It has to be bigger than that before anything happens. And that's a comment on magnitude, not on the shape of the events that are creating it. The shape of the events that are causing the stirring is really the flow separation as the flow's moving, because we're using a mechanical grid with fixed mechanical size. So there's a complex wake, reversing wake process. We didn't quantitatively measure horizontal and vertical turbulent length scales. It again's getting back to Peter's question that the thing we're interested in is what's the rate of vertical mixing. If you can measure that absolutely, does the shape, is it of first order importance, or is it, and it's certainly a part of the process that's creating it, but in the end result, it's the bit in the vertical that kind of matters. But it's certainly a subject that needs to be thought about. I agree.
Hi, Greg. Thank you for your
Correct.
talk. Yeah, so I just wanted to reinforce the point of calculating the Richardson number, right? So it all hinges around the gradient Richardson number from your talk. It seems very nicely done here, but the criteria in which how you calculate the Richardson number in the field remains a problem, I think.
Absolutely.
The resolution, and so I was just wondering if you repeated this same set of experiments with different resolutions, would you end up with the same result, right?
Right.
So that remains.
No, that's an important practical measurement question.
Right.
I didn't say it at the time, but
Yeah.
the way we set up our field measurements was that we have tight moorings with buoyancy on them. And so the spatial resolution, which we were measuring both velocity and the density field, was 1 meter in the vertical.
Right.
So that scale is always smaller than the scale of the instability. But you're right, if you had measurements at 50 meters apart, you would actually have vastly
You'll completely
different
miss out and filter it.
So you need a resolution. How fine that resolution is, ideally you should have thermistors throughout the entire ocean at, in my view, 1 millimeter apart, but that's probably not very practical. So it's a compromise.
Yeah, sure. Yeah.
But you're right. So they were 1 meter scale, which was big enough, small enough, to resolve the events we knew were occurring, because the forcing was large amplitude internal waves with forcing scales in the vertical of like 50 meters. So very large intensity compared to the measurement resolution. But it's an issue. I agree.
The second question I had for you was, if you look in the South China Sea, and I think Matthew can talk more about that, a lot of these overturns are convective, and they are mixing big time. So to sort of dismiss the convective mixing as...
that was meant to be the controversial
Okay.
bit. No, I was being mischievous. There's an interesting... if you look through the math carefully, it turns out that shear instability is based on the idea implicitly that as the efficiency goes up, you get a bigger diffusivity. Turns out convective instability is the complete reverse. So high efficiency doesn't actually mean large mixing rates. If you look at those equations, it turns out. So that's the first part. The second part is the frequency of events, which come back to Colm's question. You need lots of convective instability events before they will be significant overall contributors. And this is a large amplitude internal wave situation, a little bit like the South China Sea. And it appears as if convective instability is, quote, relatively rare, to be determined by getting clever about how to measure Richardson number once it gets up above 1 and all. But yeah, I was stirring the pot by saying we should forget about it. Man, hell, that's complicated. Let's see if we can simplify something.
One thing you didn't mention very much is double diffusive mixing. Do you think in the grand scheme of things it's not that important?
There are certainly regions of the ocean where it's extremely important. There's absolutely no doubt about it. I was and more thinking of the majority of situations where you don't have strong interleaving, away from polar regions or other regions. They can be, and of course, it's very challenging to interpret microstructure measurements in true double diffusive situations, which is another challenge. But at least in the regions where these field measurements were taken, salinity is absolutely constant. It's all temperature stratified, so it's very much dominated by there's no double diffusion in any of the physical situations I showed, even the coral reef situation. It's all as hot temperature. Okay. So yes, undoubtedly regions where that can't be dismissed.
Thank you very much. You know, now in the ocean, we normally use Argo profilers to get a global array. And so this is, have you ever thought of combining Argo with some of these more accurate sensors for, I don't know, velocity or anything? I think, you know, or even gliders would be better. So I think because, and also if you set a whole community to think about this, how would you use this enormous data set? Because if you're saying that you use that data set to do again another fit, and finding maybe regionally dependent fits and length scales or equivalent, is this the solution?
I think this gets to a technology development question, which is a good question. My third dot point up there is I really think we need to measure mean flow shear S. Argo floats don't measure S, so you can't measure Richardson number, so that's a problem. Dropped microstructure profilers don't measure mean flow shear S, so that's a problem. So my personal view is we need instruments that are actually able to profile, like Argo floats drift, but measure both temperature and other properties, of course, that Argo floats measure, as well as the mean flow shear S. Gliders have a similar problem, is that in generally they don't measure mean flow shear S locally. As the glider moves, they can certainly measure turbulence properties. But my argument really is we need to measure the shear as well as the local turbulence properties, or at least the low wave number end of the turbulence. I think those instruments don't exist, but maybe that's one thing can be discussed in this week.
Okay, thank you very much, Greg. Let's thank Greg.